So this is a really common picture. We see, in the middle there's a nucleus, and then whizzing around like planets is the electrons. And that's a really common visualization of an atom. So the general structure of the atom is similar to the structure of the solar system. That's what we've sort of grown up knowing. And then we call that the Bohr model. So at the center is the nucleus. That pink dot is the nucleus. And within the nucleus, positively charged particles called protons and neutral particles called obviously neutrons, so it kind of makes sense, can be found. So this central nucleus has protons and neutrons. And I think we've known that for a fairly long time now. Now, orbiting the nucleus are smaller, negatively charged particles, which we call electrons. And remember, there's always equal numbers of protons and electrons in any atom. Only ever electrons and protons, they're the same in every atom. They'll always be the same number. Okay? So how do we define an atom? So atoms can be differentiated using two numbers. Okay, so how do we define a particular atom is what we're saying. The mass number and the atomic number. Atoms of a particular type you can tell everything you need to know about them with two numbers, the atomic number and the mass number. And this varies. Okay, so here is a picture. Now the way this is structured depends on basically what periodic table you're looking at. So you've got always the symbol, that's always the same. But you could have the name at the bottom, which is okay. Now the atomic number is usually an integer number. Actually, it has to be an integer number. So you don't see any decimal points. And that could be at the top. So don't be confused if it is at the top. It's always integer valued and it's at the top. And the atomic mass is this decimal number, okay? And it's the weighted average of the total atomic masses of different isotopes. So don't worry too much about this number yet. We're going to get back to that in a sec. So the atomic number is the number of protons in the nucleus of the atom, okay? So the atomic number, this number, is the number of protons in the nucleus of that particular atom. That explains why this number is always an integer, right? Because you can't have 0.5 of a proton. That doesn't make sense. So this number has to be integer valued, and that's why, because it's the number of protons in the nucleus. So all atoms of the same element will have the same atomic number. Every atom of the same element will have the same atomic number. And so that tells you that every element is defined by the number of protons that it has. So oxygen will always be oxygen if there's 8 protons. So anything with 1 proton will have to be hydrogen. Anything with 2 protons has to be helium. So you can see that's how we define atoms. Now the mass number, which is not listed here, it's also given the symbol Z, is the number of protons plus the number of neutrons. So it's the number of protons, which is the atomic number, plus the number of neutrons. So that's what the mass number is. It's very, very close to the atomic mass, though it does vary a little bit. Very, very close, but not quite the same. Now the mass number separates different isotopes of the same element. We have another differentiation called isotopes, and these isotopes have different neutrons, different numbers of neutrons in their nucleus from one another. Okay, so for instance, we can have carbon that has 6 neutrons, could have 7 neutrons, or 8 neutrons. But that doesn't change the fact that it's carbon. It's just a different form of carbon, and we call that a different isotope. So we use the mass number to separate isotopes from one another. And then we can clearly define any substance that we find in the planet, or in the universe even. So boron has a mass number of 11. Determine the number of protons and neutrons in the nucleus. So the mass number is 11. So we need to think about this very carefully. So let's consult our periodic table. We know its mass number is 11. You can see this atomic mass is pretty close to 11, and there's a reason why it's different, but we'll cover that in future lessons. So boron here is there, and the mass number is the number of protons plus the number of neutrons. So if you're with me so far, this is okay, because we're just looking at our periodic table now, nothing fancy. Now we know the atomic number, the number of protons, is the atomic number, and it's here. It's always the integer number. The number of protons, or the atomic number, is 5. So the number of protons is also 5. So we put that into our equation. So 11 equals the number of protons, which is 5, plus the number of neutrons. This should be very clear now how to solve this, because we're all very clever math students. The number of neutrons would just simply be 11 minus 5. which is 6. Okay, and that's how we work these things out. We just need our periodic table and at least one of the unknowns, okay, which is usually the mass number. So if the atomic number defines a particular element and the mass number defines an isotope, define the term isotope. Okay, so I may have brought this up in passing in this lesson, but we're going to have a very formal definition of an isotope now. So isotopes are atoms of an element that have differing numbers of neutrons to one another. For example, carbon can have 6, 7, or 8 neutrons. Each of these atoms is an isotope of carbon. The one that has 6 is considered an isotope of carbon. The one that has 7 is an isotope of carbon. And the one that has 8 is also an isotope of carbon. So you can see that they're just different atoms with differing numbers of neutrons. And that's all an isotope is. So briefly define what an atom is. So we may have covered what the structure is, but we need to know what an atom actually is. So an atom is the smallest unit of an element. Okay? An atom is simply the smallest thing that you can get, smallest indivisible object of an element. It cannot be subdivided into smaller particles and still retain characteristics of that element. So the first part of that sentence is deceiving because you can split an atom into subatomic particles. You can have protons, neutrons, and electrons. But the difference is that if you were to do that, none of those particles would retain the chemical characteristics of that element. So for instance, if I took hydrogen, let's make it different, helium. It's like helium. It has 2 protons, 2 neutrons, and 2 electrons. If I was to break all of them up into their parts, neutrons, protons, and electrons, they don't share the properties of helium. They are just protons, neutrons, and electrons. So they're not the smallest thing that retains the chemical characteristics. And that's what an atom is. The smallest thing that an element can be, that still retains all of the chemical characteristics of the element. So that's an important distinction that you want to make when answering, sort of these defined questions.